In this chapter, we've been learning about different reaction types. We've learned about precipitation reactions and acid-base reactions, and at the level of a molecular equation, those are both exchange reactions. The third kind of reaction we're going to learn in this chapter are oxidation-reduction reactions, and those are often called redox for short. So the red comes from reduction, and the ox comes from oxidation. That's a redox reaction. These are also called electron transfer reactions, and I like that name because it emphasizes the nature of the chemical change. Just like an acid-base reaction is a proton transfer reaction, these redox reactions are going to be electron transfer reactions. We're going to see the electron going from one thing to another. When we looked at precipitation and acid-base reactions, we saw that we could predict the products of the reactions. We won't be able to do that in redox reactions. There's a great variety of products you can get. So I'm always going to have to tell you what the products are. Your job will be to understand the nature of the change once I do. So let's look at a particular reaction. We're going to combine sodium metal, which you've probably never seen. That's sodium metal, not sodium plus ions. And there's a picture of it here. It's a soft, shiny metal, and it's stored under oil because it reacts so vigorously with air. After this video, you'll see that I'm posting a link to a YouTube of the actual reaction between sodium metal, which is very reactive, and chlorine gas. I'm too scared to do it for you as a demonstration, even if I was in front of you. So let's let YouTube do it. And the product is sodium chloride, or table salt. So I've written the reaction here. It's not balanced yet. We just got the identity of the substances. I can balance it quite easily. What we want to do is prove that this is a redox reaction, an electron transfer reaction. So let's see what the charges on these species were before reaction and after reaction, so we can see where the electrons went. The charge on the sodium is 0. That's elemental sodium, no other kind of atoms present. So because the whole thing must be neutral overall, each sodium atom must be neutral overall. Similarly, in elemental Cl2, each atom has 0 charge. But in the product, sodium chloride, I see metal together with nonmetal. That's an ionic compound, so it contains ions. It contains charged particles. The sodium is 1+, and the chloride is 1-. So now I can keep track of what happens to the electrons. I can see that the sodium went from 0 charge to +1. It lost a negative electron. Now, how do I define that as either oxidation or reduction? In high school, you might have learned a little memory trick. I hate tricks, but this one works so well, I'm going to keep it. You may have learned that Leo the lion says grr. And what that tells me is that the loss of electrons is called oxidation. So sodium lost a negative electron to become positive. The sodium is oxidized. It underwent an oxidation. Now, it lost that electron. The electron must have gone somewhere. The chlorine went from no charge to having a negative charge. It gained a negative electrons. And the little trick tells me that the gain of electrons is called reduction. So that the chlorine underwent a reduction, it is reduced. Oxidation and reduction always happen together. The electron has to be transferred from one thing to another thing. So that's why it's called oxidation reduction, or redox for short. Now, some of you learned Leo says grr. You might have also heard oil rig in high school. Oxidation is loss, reduction is gain, whatever works. You know me by now, though. I don't like tricks. I'll tell you a better way to know very, very soon, but we got to start somewhere. Now, one more thing on this slide. I've talked about things that are oxidized and reduced, but now I want to talk about oxidizing agents and reducing agents. An oxidizing agent causes oxidation. So the chlorine here caused the oxidation of the sodium. I would say then that the chlorine is the oxidizing agent. The chlorine causes oxidation while it gets reduced. And similarly, the reducing agent is sodium. The sodium causes the reduction of the chlorine. It is the reducing agent. It causes reduction while it gets oxidized. So all's well and good in this case. I can see the charges on the species changing. I can see the electron transfer. But some cases are more subtle than that. Let's look at another redox reaction. Here's an oxidation reaction. We've got methane and oxygen. And this is a combustion reaction. So this time I do expect you can predict the products. We know that combustion is reaction with oxygen gas to produce carbon dioxide and water. And I'll quickly just balance that. That's not the fun part. Now, I know that this is a redox reaction. Another way to define oxidation is reaction with oxygen. However, I can't see the electrons moving here. I don't have any charged species. I don't have any ionic species. These are all molecular. So here's how we're going to decide whether redox happened or not. We're going to see if there's a change in oxidation number. Now, you might have memorized some rules for oxidation numbers in high school, but memorizing is evil. It never works. I suspect if you memorized it then, you couldn't tell me about it now. I think if we define clearly what oxidation number means, we won't need any rules. All that oxidation number is the charge the atom would have if the bonding were ionic. Charge the atom would have if bonding were ionic. So let me illustrate that with my favorite covalent compound, water. That's two nonmetals. That's covalent. It's not ionic. It's not charged. But I can assign oxidation numbers to those atoms. So I'm going to imagine on paper, you can't really do this, that it's ionic. I've got oxide ions and hydrogen ions. Now, if it were ionic, you know how to predict its charge from its position in the periodic table. You look at your periodic table and you would see that an oxide ion has a -2 charge. And you know a hydrogen ion would have a +1 charge. So that means in the original neutral molecule, the oxidation number for oxygen was -2, and each hydrogen is +1, because the oxidation number is what the charge were if the bonding were ionic. A little subtlety here. I write the charge with the 2 and then the negative sign. But the oxidation number is a regular number, like in math class, the negative sign goes first. Not to worry too much about that subtlety. Now, with that understanding, I want to go to the rules that you learned when you were in high school and show you don't need them anymore. Here are the rules for assigning oxidation numbers. I've left blanks there because I want you to pause and figure out what the rule should be based on our definition of an oxidation number. So rule number 1 is the oxidation number for an atom in its elemental state is. Well, let's go back and look at the examples on the previous slide. That oxygen is in its elemental state, O2. There's only one kind of atom present. And what's the oxidation number of that? Well, that's not charged at all. The whole thing is neutral overall, so each atom must be neutral overall. That oxidation number is 0. The oxidation number for an atom in its elemental state is 0. All right, rule number 2, the oxidation number for an ion. Well, what's the definition of oxidation number? It's the charge the ion would have if it were ionic. So when it is ionic, the oxidation number is just the charge on the ion. Rule number 3, the oxidation number for oxygen in a compound is, well, what's the charge on an oxide ion? From its position in the periodic table, it's -2. Now, you probably memorized that in high school, but you don't have to once you know what oxidation number means. Similarly, the oxidation number for hydrogen in a compound is usually +1, as we saw in our consideration of water on the previous slide. That's going to be good enough for us. I put these words usually here so that you don't find later that I lied to you. Usually it's this charge, but there are other bonding situations where it could be different. I'm not going to trick you though. That's what we're going to find in our examples. Now, I'm not going to show the oxidation numbers for other elements. They are very different in different compounds. So what we're going to use instead to find the remaining oxidation numbers is that the sum of the oxidation numbers is the charge on the species. The oxidation number is the charge the atoms would have if they were ionic, and those charges have to add up to the overall charge. All right, so now I'm going to go back to the combustion of methane on the previous slide. We won't even need to look at these rules for you to be able to assign oxidation numbers. All right, so we've already assigned the oxidation number to the elemental oxygen. That was 0, no charge. Now, methane. I don't know carbon, but I do know hydrogen. The oxidation number for hydrogen in a compound is +1. Oxidation number for hydrogen in a compound is +1. The other one I know is what the oxidation number for oxygen in a compound is. -2. -2. Now let's look at the water here. Here's a beautiful thing. Water is neutral overall, and if I add up the oxidation numbers, that's what it comes out to be. Very reassuring. Each hydrogen is +1, but I have 2 of them. So that's +2 for both hydrogens, and -2 for the oxygen, neutral overall. The last rule we came up with oxidation numbers is that the overall charge on the species is the sum of the oxidation numbers. So we can use that to find the oxidation numbers of the carbons. What's the oxidation number on that carbon since methane is neutral overall? Pause the video. I think it's -4 because -4 for the carbon plus 4 times +1 for the hydrogen is neutral overall. What about the other carbon? Pause the video. I think that carbon is +4. +4 for the carbon, plus 2 times -2, 0. Carbon dioxide is neutral overall. So now that I can see the oxidation numbers, I know for sure it's a redox reaction. It's only a redox reaction if the oxidation number changes. This carbon changed from -4 to +4. Is that an oxidation or a reduction? If I go from -4 to +4, that's getting less negative. I'm losing negative electrons. And according to Leo says Gur, less electrons is oxidation. The methane is oxidized. Hey, that makes sense. Historically, the meaning of oxidation was reaction with oxygen. Methane reacts with oxygen, it gets oxidized. We've generalized the definition of oxidation since then, but I'm glad it works in this case. Now, if the methane got oxidized, something else must have gotten reduced. We're looking for another atom whose oxidation number changed, and it is the oxygen. Where's my pen here? Oxygen 0 goes to oxygen -2. It got more negative. It gained negative electrons, and gain of electrons is reduction. So there we go. We've got a new way to define redox reaction, change in oxidation number. In the first examples, I taught you that Leo says Gur. That's a trick to remember what oxidation and reduction is. But now that we understand the nature of the change, I can give you a more useful definition of oxidation. Oxidation turns out to be an increase in oxidation number. Yeah, that makes sense. More oxidized, oxidation. Conversely, reduction is a decrease or a reduction in the oxidation number. The last thing I want to do in this video is actually show you some redox reactions taking place so you can see the importance of oxidation number. If I have different oxidation numbers for a given element, it really changes its chemistry. We've got to be really careful with charges and oxidation numbers. So let me set up a demonstration for you. So I've got a solution here of potassium permanganate, and I know you don't know what that is. That is KMnO4. Nice deep purple solution. I want you to determine the oxidation number of the permanganate, of the manganese in the permanganate. Again, KMnO4. I think you should find that it is +7. That's a high oxidation state. Now, this is a deep purple solution. I'm going to pour some of that into a series of beakers, and I'm going to add a reagent to them. I've got my beakers off to the side here. I'm going to put 50 milliliters of solution in each one of my beakers. Now you will see the equations for the reactions I'm going to try on the slide in your pre-lecture notes. I'm going to add sodium hydrogen sulfite solution, which is colorless to each one of them. But I'm going to use slightly different conditions. I am going to do one of these in a neutral solution, no acid or base added. I'm going to do one of them in acidic solution and one of them in basic solution. And you'll see what I promised you before. There's no way to predict the products. They have to be given to you, but they are given to you in your pre-lecture notes. Okay, so in the first one, I'm going to make it acidic. I'm going to put some 1 molar sulfuric acid that I have in my graduated cylinder. And here's the beaker. I'll give it a little stir with my glass rod. So we've got a purple solution that's acidified. Now, here comes my solution of sodium hydrogen sulfite. And I'll add some to that and give it a stir. Needs a little bit more. And you can see that it became colorless. Now that doesn't mean the manganese went away, it just means I've turned it into another form of manganese. And when we look at these equations, you will see what form that is. Remember, the big message I'm trying to send here is that the charge or oxidation number on an atom really changes its chemistry. All right, that was an acidic solution. Now let's see what happens when I do it in basic solution. I've got another beaker. Starts with just the plain old potassium permanganate solution, and I'm going to put some sodium hydroxide solution in there to make it basic. Stir it up. And again, I'm going to add some sodium hydrogen sulfite solution. And I stir that up. I don't know if you can see around the edges of the beaker, see what color that foam is? That's green. That's a third different oxidation state of manganese. So again, if I change the oxidation state, that really changes the chemistry. Last one, I'm going to do just plain old neutral. I've got just the sodium hydrogen sulfite solution. We'll add that to the neutral solution. We give that a stir. And what I'm getting there, I think you can see, is a brown sludge. If you've ever worked in the lab with potassium permanganate solution, that brown sludge gets all over your fingers. You go home with brown fingers. So again, a fourth oxidation state of manganese that shows the charge really matters. Now we'll come back and look at the equations. So here are the reaction equations that go with the demonstration I just showed you. In each case, we start with purple potassium permanganate. Now I've written these as net ionic equations. I've left out the K plus spectator ion. That's the purple permanganate. The oxidation number of this manganese is +7. I figured that out because I knew each oxygen was -2, and there were 4 of them altogether. The net charge was -1, let's double check, +7 for the manganese, +4 times -2 for the oxygen, -1 overall. Good. So each one of these manganese starts as +7 in the purple solution. Now we're going to add the hydrogen sulfide ion. And in one experiment, we did it in acidic solution. In one experiment, we did it in basic solution. And finally, we did it in neutral solution. But it turns out there was just enough base to make it go the way that we saw. So let's go in the order that I demonstrated them, which is not quite this order. First, I did it in an acidic solution, and we observed it turned colorless. I have to tell you authoritatively that the product there was manganese 2+. And what's its oxidation number? Well, oxidation number is the charge it has if it's ionic, and it is. So that oxidation number is +2. I went from manganese +7 to manganese +2. I reduced the oxidation number. That was a reduction. And therefore the hydrogen sulfite must be a reducing agent. The next demonstration I showed you was in the strongly basic solution, and it made green. The ion responsible for that green color is MnO4 2-. Now that, notice the charge. The charge is so important. If it's only -1, it's purple. If it's -2, it's green. And that was one of the big points of the demonstration. I wanted to show you that the charge affects the chemistry so much. We've got to care about the charge. Now, if we work it out, the oxidation number of this manganese is +6. Again, another oxidation number, but it's still a reduction process. I ended up with a lower oxidation number than I started with. Finally, I did it in neutral solution. There needed to be a trace of base that was around in that solution already. The last one we observed a brown precipitate of MnO2. And the oxidation number there is +4. So we can see that these are all reduction reactions, but we ended up with different oxidation numbers. The oxidation number determines the chemistry. The charge determines the chemistry. So we're never going to forget the charge ever again.